Hi, and welcome to our lesson on analog to digital converters. Microcontrollers often need to measure real-world quantities. For example, our digital thermostat has to measure temperature. For that, it uses a temperature sensor. The sensor sends out a voltage that's proportional to the temperature. That's an analog voltage. Okay, over here in this picture on our left we see an analog voltage, and you can see it goes smoothly from 0 to 5 volts. There are no discrete steps in there. If you ask a mathematician how many points are on that line segment, he'll tell you an infinite number. That's an analog quantity. Digital value, on the other hand, is a bunch of discrete steps. So we see over here a digital quantity that has 8 discrete steps, and so each one would be proportional to one place on this analog signal. Computers are digital. They don't know what to do with analog voltages, so we have to find out how to take an analog voltage and what we call digitizing it. And that means converting it into a number so that the computer can deal with it. So as we said before, sensors produce an analog voltage output. So here we see an oxygen sensor, an O2 sensor that might be in a car's engine control unit, and it produces an analog output. That gets fed into an analog to digital converter, or an ADC, and coming out of the analog to digital converter is a binary number that gets fed into the microcontroller. So here we see a very small analog voltage. The binary number is going to be proportional to the analog voltage. So here we see a very low analog voltage, and it produces a small binary number. Here we see a large analog voltage, and it produces a really big binary number. If we look at the range of an analog to digital converter, let's say our input signal can be anywhere from 0 to 5 volts. So a reference voltage would be 5 volts and 0 volts. So if our range is 0 to 5 volts, and it's an 8-bit analog to digital converter, an 8-bit converter can produce numbers from 0 to 255. That's the biggest number you can represent with 8 bits. So our output, our digital output, is going to be proportional to the analog input. So let's say our analog sensor, our sensor produced a 2-volt output. So that's the input to the A to D converter. So the question is, what's the digital output going to be? What is this number going to be? Well, it's a simple proportion. So we're going to set up a simple proportion. Our voltage in divided by 5 volts is the same as the ADC out over 255. So here's our voltage in compared to 5, ADC out compared to 255. So if we do a little math on that, okay, you know how to solve a proportion. You cross multiply and set the two sides equal to each other. Do a little more algebra. This is why we make you take math class. Okay, do a little more algebra, and we can see that the analog to digital converter output is going to be equal to 255 divided by 5 over the voltage in. So our signal before we said was 2 volts. So a 2-volt input to the ADC is going to produce what as a digital output, as a binary output? Well, we plug the numbers in, we plug 2 volts into the formula here, and we come up with a number of 102 decimal, and if we convert that into binary, that's what the binary number would be. So the analog output is just proportional to the voltage in. So if our signal was 2.5 volts, what would the digital output be? Well, you can probably see that 2.5 volts is half of 5. Well, what's half of 255? If you do the math, you'll see that it's 127.5, and we don't deal with fractions of numbers, so we're going to round that to 128. I'll let you convert that into binary on your own. Let's say our ADC was, instead of 8 bits, was a 10-bit ADC. That means each of its steps are going to be that much smaller. So if we have a 10-bit number, with 10 bits we can represent numbers from 0 to 1023. So let's say our analog voltage was 1 volt. What's the digital output going to be? Well, it's the same kind of a proportion, but in this case 1 volt compared to 5 is going to be proportional to our unknown compared to 1023. So plug our numbers in here again, do our little proportion, and what we see is that our output is going to be the number 205. Okay, now that should make sense, because if you think about this, 1 volt out of 5, that's 1/5. Well, what's 1/5 of, let's just round that to 1,000. What's 1/5 of 1,000? Well, it's 200. So 1/5 of a little more than 1,000 is going to be a little more than 200. And that's what we've got here, 205. Okay, so it's always a good idea to do a little sanity check. Does that number actually make sense? Is it about 1/5 or whatever the number is? Okay, always look at that. Resolution means the smallest change in voltage that an ADC can represent. I'm going to call it how small of a step size is this. Okay, so each step represents what voltage, what change in voltage. So if you look over here, you'll see this is a 2-bit analog to digital converter. That doesn't mean it costs 25 cents. It means it produces a 2-bit output. Okay, you would never see a 2-bit ADC in the real world because, as you can see, it's not very useful. But it's useful for just demonstration. So with a 2-bit value, you can produce 4 different values, 4 discrete values with a 2-bit number. So my resolution would be 1/4, since I have 4 steps, would be 1/4 of my total range. So 1/4 of 5 volts is 1.25 volts. So what that means is every time I increase my binary number here by 1, that represents a jump of 1.25 volts, which, as you can see, is not a very precise measurement, is it? Let's say I did a 3-bit analog to digital converter. With 3 bits, I have 8 possible outputs, or 8 possible values. That means each step is going to be 8, or 1/8 of the total. So what's 1/8 of 5 volts? My resolution there would be 0.625 volts, or 625 millivolts. If this were a 4-bit ADC, the resolution would be, well, with 4 bits I can represent 16 steps, so it would be 5 volts divided by 16, or 0.3125 volts. If it were an 8-bit ADC, well, for one thing, I'm not going to draw 256 steps here, but an 8-bit ADC can produce any one of 256 different numbers. So I would take my 5 volts, divide by 256, and I would get a resolution of 0.0196 volts, or about 20 millivolts. So there you have the basics of analog to digital converters. In part 2 of this lesson, we'll take a look at the built-in analog to digital converter that comes with the PIC microcontroller. Bye.